Welcome. This is R. Premananda, Assistant Professor, Government Engineering College. Regarding this lecture regarding the Dsp Lab, as I am handling the Dsp Lab in Government Engineering College, Haveri, I want to explain the theoretical proof of the experiments so that using the DFT property experiments, according to this, in this today's lecture, we are studying the properties of the DFT. As per the syllabus, we have got the two property. One is linearity and another one is the perceval property. So now in this lecture, we are going to study about the linearity property. See that if x1 of 1 is applied to DFT, and the resultant will be in the x1 of k. Similarly, x2 of n will be the x2 of k. Then a1 times the x1 of n plus a2 times the x2 of n applied to DFT will get it as a1 times the x1 of k plus a2 times the x2 of k. See here notations used. x1 small x is the time domain signal and the capital X is the frequency domain signal, or we call it as DFT signal. Okay, here is regarding the linearity property. How we got this one? See, applying the T stands for DFT transformation. Here according to this DFT transformation means what we are applying, whatever signals in time domain will add first and then transform to the DFT, and their result is equal to the individual. Okay, x1 of n transformed and we got the x1 of k, and their plus x2 of n is transformed to x2 of k. Their individual summation is equal to the total summation. It will prove the linearity property of the DFT. For that, I will have an example and I'll tell that according to A1, so for the sake of simplicity, I will consider A1 is equal to 1 and A2 is also 1. And I will consider x1 of n, the value of x1 of n is 1, 2, 3, 4, and the value of x2 of n is all 1. For the sake of simplicity, I am considering these values. Okay, first I will solve the LHS. This part, that is what is that? First I will perform the summation and I will transform. I will apply the transformation. I will solve this one first. So that a1 into x1 of n is nothing but, see, a1 is the value 1, x1 of n is 1, 2, 3, 4, and their result is similar 1, 2, 3, 4, because 1 multiplied by anything results in the anything. Similarly, a2 x1 of n is again 1 multiplied by what is that, 1, 1, 1, 1, will get the result as 1, 1, 1, 1. So now we'll add this. Okay, you will add this. This becomes a1 times the x1 of n plus a2 times the, so this is x2 of n, x2 of n, and the result is, see, both is 1 row 4 column. Okay, addition, okay, we can perform the addition or regarding this, it will get this 2, 3, 4, 5. See, I have not applied the transformation. Now I apply the transformation of a1 x1 of n plus a2 x2 of n. It is DFT transformation. So that we have got the DFT signal as, okay, you know that what is this? This is x, that is 2, 3, 4, 5. Numerically, the DFT can be written in the matrix form as shown here. Okay, DFT in matrix can be written as shown here. See, this is the x1 is the order of 1 cross 4, 1 row 4 column. This is the order of 4 row 4 column, and the resultant will be 1 row 4 column. 1 row 4 column. Okay, see the matrix multiplication. This 2, 3, 4. We have to perform this in this matrix multiplication concept. Okay, like this. Row multiplied by with the columns. On doing so, we will get the result as shown here. That is 2 into 1 is 2. So that 2 plus 3 into 1 is 3. 3 plus 4 into 1 is 4. 4 plus 4 and 5. See, first row and column is finished. Similarly, first row, second column, that is nothing but 2 2 minus 3j plus 2 minus 3j minus 4 plus 5j. Okay, next row on the third column, that is 2 minus 3, 2 minus 3, 2 minus 3 plus 4 and minus 5. And the fourth row on the fourth column, that is 2 plus 3j minus 4 minus 5j. Okay, plus 3j minus 4 minus 5j. Okay, and this can be written as separately. 2 plus 3 plus 4 plus 5 is nothing but 5 plus 5, and the answer first one is 14, comma. This is minus 2 plus 2j, and next is minus 8 plus 6, that is minus 2, and this is minus 2 minus 2j. This is the result of the transform of a, that is DFT of a1 of x1, a1 times the x1 of n plus a2 times the x2 of n. This is the LHS part of the equation. If the same result is obtained in the RHS part, then we can conclude that the given DFT holds good the linearity property. So we will solve that the RHS part. Okay, we will solve the RHS part. What the RHS part tells, okay, that is a1 times the x1 of k plus a2 times the x2 of k. x2 of k. Okay, means first you have to perform the DFT function. The x1 of n should be converted to the x2 of n. So see, a1 is a coefficient, a1 is 1, a2 is also 1. So their presence can be neglected because it's 1 multiplied by anything will result in an anything. So that x1 of k is obtained by x1 of n multiplied with this DFT matrix plus x2 of n multiplied with by the DFT matrix. Okay, I'll write the DFT matrix. Okay, the DFT matrix has been written here. Okay, what is that? Okay, x1 of n, I'll replace that x1 of n. What is that x1 of n? That is 1, 2, 3, 4. And what is that x2 of n? x2 of n is 1, 1, 1, 1. And the result, see row multiplied with the column. The first it is 1 plus 2 plus 3 plus 4, comma. And for row in the second column, that is, I'll write below, that is 1 minus 2j plus minus 3 plus 4j. And this row, third column, that is 1 minus 2 plus 3 minus 4. Okay, and the row on the last column, that is 1 plus 2j minus 3 minus 4j. Okay, similarly plus, see all are 1, so that this can be written as 1 plus 1 plus 1 plus 1. Okay, first row, this row in first column. Okay, and again this row in the second column, 1 minus j minus 1 plus j. Okay, next this row in third column, 1 minus 1 plus 1 minus 1. And this row in the fourth column, that is 1 plus j minus 1 minus j. Okay, here. So this can be written as, the values are written as, this 1 plus 2 plus 3 plus 4 is 10, and next is 1 minus 2j plus 4j results in plus 2j. So this is minus 2 plus 2j plus 1 and plus 3 is 4, and minus 2 minus 4 is minus 6. So the answer is minus 2. This is nothing but 4 minus 6 is minus 2. This is 1 minus 3, okay, going to get it as a minus 2, plus 2j minus 4j going to get it as minus 2j, plus, okay, plus, here this is 1 plus 1 plus first one is 4, and 1 minus 1 is 0, minus j is 0, minus j plus j is 0. Similarly, this is all are 0. And their result, I will add this one, the summation. This can be written as 14, comma, minus 2 plus 2j, comma, minus 2, comma, minus 2 minus 2j. See, what is this? This is the result of the RHS, that is A1 times the x1 of k plus A2 times the x2 of k. So, by comparing these two results, see, by comparing these two results, this result, we can say that the transformation or DFT of A1 into x1 of n plus A2 into x2 of n is equal to A1 times the x1 of k plus A2 times the x2 of k. Means that DFT holds good the linearity property. Now, another property of the DFT is the Parseval theorem. Parseval theorem states that summation of 0 to n minus 1 x of n square is equal to 1 by n times the summation of k is equal to 0 to n minus 1 x of k square. That is nothing but the energy of time domain signal is equal to the energy of the frequency domain signal. We have to prove that one. Okay. See, if you start from the 0, it will the upper limit is n minus 1. If you start from the 1, the upper limit will be the n. Okay. If it is 0 if you start from 0, the lower if it is the lower limit is 0, then the upper limit will be n minus 1. If the lower limit is 1, the upper limit will be the n. Okay. Now we'll consider an example. Okay. Saying that x of n is equal to 1, 2, 3, 4. I am taking this. Okay. And the length of this, I will call this omega, it is the 4. The length of this is 4. Okay. According to this formula, that is LHS, what is that? That is summation n is equal to 0 to n minus 1. See, this is x of 0 and x of 1, x of 2, and this is x of 3. So, x of n whole square, okay, this can be released. This can be written as x of 0 square plus x of 1 square plus x of 2 square plus x of 3 square. See, this model is absolute values. This is nothing but 1 square plus x of 0 is 1. So 1 square plus x of 2, 1 is 2. So 2 square, x of 2, that is third position, that is 3, that is 3 square, and this is 4 square, and the result is 1 plus 4 plus 9 plus 16, and the answer is 30. Through LHS, we get the answer, it as 30. Okay. Next, for the next concept, we have to find the x of k. See here x of k means it's the frequency discrete Fourier transform signal. See how to find the x of k? Okay, already we have discussed that for the answer 1, 2, 3, 4 applied for the DFT, that with the matrix and the answer of this is already obtained, that is 10 comma, and while discussing the linearity property I have shown the answer. 10 comma minus 2 plus 2j comma minus 2 and minus 2 minus 2j. This is the answer of the DFT convoluted signal. Okay. See, and these are, we have both real and imaginary both. If you want that, okay, what is this? This is x of k. What we got? This is x of k. So if you want the modulus of x of k, you can write this as 10 comma square root of 2 square plus 2 square, that is nothing but imaginary real square plus imaginary square, comma 10 square, that is square root of 10 square, okay, square root of minus 2 square, comma square root of minus 2 whole square plus 2 whole square, and their result will become Okay, its result will be okay. See, this is x of k, the magnitude of x of k. Now I will apply. See that RHS is equal to 1 by 4 times the, I will release the summation, I will write the x of 0 whole square plus x of 1 whole square, or x of 1 square 1 whole square plus x of 2 whole square plus x of 3 whole square. Okay, 1 by 4 as it is. What is that? X of 10 whole square is nothing but, okay, it's nothing but square root of 100 square whole square plus square root of 2 square plus 2 square, it is 8 whole square plus square root of 4 whole square plus square root of 8 whole square. Okay, see in this, so what is this? Here only I can write, this is nothing but square root of 10 square is nothing but 10, it is square root of 8, it is square root of 4, it is again square root of 8. See, this is again, this is what is that? This is simply the absolute value of x of k. In this RHS, this is whole square is there, that whole square I have taken here. Okay, square root of 10 square into whole square, square root of 8 into whole square, square root of 4 into whole square, square root of 8 into whole square. Okay, now I can write this as RHS is equal to 1 by 4 times the square root and square cancels, the first term is 100, 10 square is 100, square root and square cancels, here square root and square cancels, the second term is 8, the square root and square cancels, the third term is 4, and again it is going to be the 8. The 100 plus 20, it's 8 plus 8, 16, 16 plus 4, 20, 100 plus 20 is, okay, this is 120, and 120 divided by 4 is, this is 30. See, RHS is 30, and the LHS, what we have this obtained, this LHS is also 30. LHS is also the 30, which means that LHS is equal to RHS. That is nothing but the square root of n is equal to 0 to n minus 1 x of n whole square is equal to 1 by n times the summation of k is equal to 0 to n minus 1 x of k whole square. This is the Parseval theorem. Thank you.